Can you hear me?
Yeah. Yes, we can hear you loud and clear.
Where is everyone? Okay. So I'm happy to introduce today's speaker, which is Adrien Tavernier. He's an astrophysicist, and oddly enough, as an astrophysicist and also an engineer, as he likes to describe himself, he's currently pursuing his PhD in the Department of Earth Science and Geoenvironmental Science at the University of Bari in my team under my supervision, even though sometimes it's not clear who's supervising who. And you will realize it soon enough, because Adrien likes to play with very, very complex problems. Is a research at the moment focused on the detection of potential biosignatures using hyperspectral remote sensing techniques, clearly with astrobiological implications for the applications to planetary exploration. So I'm really glad that he accepted this invitation, and I hope that you will understand this fascinating topic. Adrien, over to you.
Okay, so yeah, you can hear me fine?
Yes, go ahead.
Yes, we can hear you.
Okay, so first, thanks a lot for the invitation to speak about this kind of thematic. And Fulvio, thanks for the introductions. And so the topic today will be the challenge or the challenges of detecting extraterrestrial biosignatures. So just to go back, in fact, to the illustration you have here for these presentations, it is split into two parts. On the left part, you have the microscopic, in fact, representation of photosynthesis. This is a cell, and within this cell, you can observe chloroplast, and within the chloroplast, you have the chlorophyll, which allows photosynthesis. And on the right panel, you have, of course, a picture of Earth, what the scientists called the breath of Earth, because you can see the vegetation on the continents, clouds, of course, and in the ocean, phytoplankton. So I will go back, in fact, at the end of the presentations to this representation of Earth, because perhaps in the future, it will be the best way to detect life on other planets. So here, with a focus on exoplanets. There is also something which is really important here, and which would be, in fact, a kind of philosophy of this presentation. It's going from the microscopic scale to the macroscopic one. So to understand, in fact, the global scale of a planet, it's necessary to understand, in fact, the macroscopic scale. So this is, in fact, what is called here the guiding principle, the first one. So we will try always to go from the macroscopic scale to go to the global scale, or to the global scale to the microscopic one. And typically, we will focus on the interaction between light and matter, okay? And we will go almost every time to the elementary composition of matter. You have here a quote of Richard Feynman, who was a physicist who won the Nobel Prize according to his work to quantum physics. And he was saying that if all scientific knowledge were destroyed, And if we have to keep only one sentence for the upcoming generation, which sentence will have the most information? And he said that all things are made of atoms. And I add and molecules, because we will focus mainly on molecules in this talk. So when we are coming back, in fact, to the macroscopic scale, of course, in physics, we can go at a smaller scale of the atoms with the particles. But if we stay at this representation of the periodic table, which was created by Mendeleev, in fact, we have a lot of informations according to the chemistry, and life basically is chemistry, and we can understand a lot of things. Again, what is important here, it is the astrobiological periodic table. This is quite interesting because you can see for each element, you have on the left panel the astrophysical source, if it is based on the primordial nucleosynthesis, so from the Big Bang, or if it is directly linked to stellar nucleosynthesis, almost all the elements are produced within stars, or if they are man-made. And this is the heavier elements you have in this table, and these elements are unstable and they are man-made. And also on the right panel, you have the biological use. All these kind of elements will be used by life, or life as we know it on Earth. So this is the kind of guiding principles we will follow during this presentation. So Fulvio describe a little bit the PhD project I am working on. So there is a kind of bias also in this presentation according to my research topic. And what we try to do is spectral unmeeting. So we were using typically hyperspectral data. So you have here the difference between multispectral, which could be, for example, a camera you are using. You have 3 channels, red, green, and blue. But with the hyperspectral, we'll have hundreds of channels. So we have a much more detailed, in fact, information about light. And light typically will interact with matter, and we can see, in fact, the reflectance spectra. And for example, if we are looking at vegetations in the visible, the vegetation will absorb most of the visible light, but will reflect the green one. That is why, in fact, vegetation is green, because most of the light is reflected. Most of the green light is reflected. So according to this, also to absorption bands, we can have an idea of compositions. And the topic of my PhD is using data cube. You have here on the left a data cube. So you have some pixel like a typical camera. So you use a camera you have, for example, on your phone. Again, it's 3 channels, red, green, blue. And you're making a mix of it to reproduce what the human eyes can see. But with a cube, we have hundreds of channels. But because we have 1 pixel, which is, for example, 30 meter by 30 meter, which is a typical resolution of the hyperspectral mission on Earth, we have integrated informations. So in this pixel, we can have vegetation, soil, building. So we have to do an unmixing of these components to go back to the different components you have within 1 pixel. And the objective of my PhD is to use, in fact, the recent boom of hyperspectral mission that are observing Earth. It's quite recent. It started in the years 2020s. You have 3 missions currently in MAP, PRISMA, and PACE that are observing Earth with hyperspectral data. And the aim is to use this kind of observation on all the new algorithmic development you had according to this mission to do the reanalysis of extraterrestrial data, mainly on Mars, with the instrument Omega Crism that were launched in the years 2000 in order to detect new materials with new technology and with the help of Earth. Because on Earth, we can use also in situ data to confirm what we are seeing with remote sensing. So why I am using, in fact, the interaction between light and matter in this presentation, according to the search of biosignature, because there is a huge bias according to what I am doing during my PhD. But in fact, astrobiology, you can see, and this kind of physical approach using physics of astrobiology, you can see here, and this is a kind of bibliometric study of astrobiology that has been done in 2023. And this is multi and transdisciplinary science. So in order to do astrobiology, there is connection between physics, biology, chemistry, astronomy, astrophysics, even philosophy. So this is something which is multi and transdisciplinary science. So in the talk, the presentation I will do, there is some parts let's say I master more than others. I have to speak about biology, but I'm not a biologist. There is something also important here. You can see that the origin of life is one of the key words related to astrobiology. So there is the question of the origin. So it might go away from science, but in this presentation, we will stay with science. And there is something which is quite important, so the guiding principles too, which is called the cognitive expectation of scientific knowledge. So go with skepticism, so with no preconceptions when a scientific work is done. Then the hypothesis of realism, so reality exists independently of the person who is doing the study. Then rationalism, so it is important to use logic and the Occam principle. So the Occam principle is when we have different hypotheses, it might be the simplest one for the same result. It might be the simplest one that is the correct one. This is the Occam principle or parsimony principles. Then materialism, we can do only experiments on matter. Okay, so matter is in fact the things on which we have to do the test. Then transparency is important to sharing results and explaining methods. And exhaustiveness, we need to use all the data that are available. We cannot choose some specific data that will confirm our hypothesis. So why I am showing this guiding principle 2, or the cognitive expectation of scientific knowledge, because I will show you some example of scientific controversy according to biosignature, and where we are in fact studying in details what was the problems according to the false detection of biosignature. Some of this cognitive expectation of scientific knowledge are not respected. Also, this is kind of a matrix that can be used each day in order to see if we are reading an article, which can be an outreach article, it is really a scientific methodology that is used or not. So also, because I think we are 15 people, it's quite complex thematic. So if you have questions, don't hesitate to interrupt me. At each, there is, I think, 5 or 6 parts in my talk. At the end of each part, I will stop and I will ask if there is some question before to go to the next one. So here we are. So we can really start, in fact, the presentation after this kind of preliminary guiding part. So the outline of the presentation, we will start with the life in the universe. Then we'll speak about the building blocks of life to see directly life again as we know it on Earth. We will focus on detecting biosignature, and in this part, mainly I will use detection of false detection of biosignature. And for the conclusion, we'll go into contingency and the Fermi paradox. So first, life in the universe. So some epistemology to start, which is called the plurality of inhabited world. So you have in the center the reproduction of a book from the French astronomer Camille Flammarion, so 19th century. He wrote a very famous book, at least in France, La pluralité des mondes habités. So it was much more outreach than science. But it was in fact a kind of summary with knowledge of the 19th century of a debate that starts in the antiquity. So here on the right panel, on the left, sorry, panel, you have Aristotle and Ptolemy. So for us, they were against the plurality of inhabited world. So Aristotle has a very basic, simple conceptions of the universe. So there was the sublunar world and the world which was beyond the moon, which was perfect. And it was a geocentric approach, which was then in fact scientifically taken by Ptolemy. And Ptolemy developed the system, Ptolemaic system, with the Earth at the center and the orbits of the different planets with this kind of epicycle in order, in fact, to match the observation. For example, the retrograde motions of Mars, which was observed on the sky. And on the other side, you had Democritus here and Epicurus, so which were in fact first Democritus was in favor of atoms and also about an infinite universe and an infinite universe that can harbor a plurality of inhabited world. So then the Ptolemy system last during 13th century. So, and with the development of the modern science in Europe, there was a kind of shift of paradigm shift of paradigm, sorry, with Copernic. So from the geocentric approach to the heliocentric one. And then with Kepler and Galileo, it was possible also to adapt the circular motion and the epicyclic to the elliptic motion of planets around the suns. So, and it is the start of modern science and also the understanding of the different scale of the universe. So you have here kind of different representation of the different scale from the particle to the nucleus, to the Earth, the different planets, the galaxy, the group of galaxy. I think here there is an inversion between the last one and this one. Here it will be the universe, and here the group of galaxy. So when you have this kind of proportion that you understood that, for example, in a galaxy, you have hundreds of billions of stars, and that the sun is a star. Statistically, it might be reasonable to say that, okay, life appeared in the solar system, but there is a billions of solar systems in the galaxy, so it might be probable, the probability might be not so low to have life in other places. And it was in fact statistically developed by Francis Drake during the 20th century. So with the famous Drake equations, in order to to do a quantification of the probability of development of life in the galaxy, but also not only life, but also civilizations. So you have different parameters in these equations. The rate of formation of star in a galaxy, the fraction of star which will harbor a planet, the number of planets which will have, let's say, an environment that can sustain life, and so on. Okay, so when the Drake equation was developed, none of these terms had a kind of observational counterpart. Now, what we have a kind of good approximations of the first two and perhaps the third one. Okay, and then we can play, and you can do kind of statistic to see if there is a high probability for a galaxy to harbor life or other civilization than the human one. So according to this first part, life in the universe, so there is a kind of, let's say, we can say a controversy between people or scientists who will say that life is a very rare phenomenon, and other scientists that will say that, in fact, no, life is quite common, and we might be, it might be possible to detect life in our galaxy or in the universe, more general. So this is the end of the part one. Do you have any question? No? Okay. So the second part, the building blocks of life. So we'll continue to go into the scientific development that lead to astrobiology and the search of biosignature detections. So the first things to do is to try to define life. What is life? So when you're asking biologists, you are asking 10 biologists, you will have 10 different definitions. Okay, so it might be interesting to use one which has been in fact accepted by NASA. And NASA is defining life as a self-sustaining chemical system capable of Darwinian evolution. So two important group of words here: self-sustaining chemical system and Darwinian evolutions. So self-sustaining chemical system, so this is kind of reference of thermodynamics, physically speaking. It means that life will be able to get energy and matter from the environments and to use it. So you have here an example of a candle. So a candle is a self-sustaining chemical system because when you have matter, the candle will have the opportunity, in fact, to consume energy. And when you remove, in fact, the matter, you stop everything, thermodynamics equilibrium. And in fact, thermodynamics equilibrium for life is equivalent to death. So death is a thermodynamic equilibrium. So life is a thermodynamic system, physically speaking, which is always in disequilibrium. And then this chemical system has to be capable of Darwinian evolutions. So you have here a kind of symbology of what is not Darwinian evolution, because this kind of representation is false according to Darwinian evolutions. So here, if we are considering human and in fact, here, if we are considering the animals, monkeys, this is in fact, or we have to do the classification. So you have here Darwin, which was developed, in fact, the Darwinian evolutions. So the Darwinian evolutions, this is based on random mutations. So it means that here, and we'll speak about it at the end of the presentation, that contingency is really important. So you have, during the geological times, mutations, and the mutations will allow some group to better adapt themselves to the environments. And if they adapt better to the environment, they have more chance, in fact, to have reproductions, and then to be into this environment. So this is how Darwinian evolution works. And in order to have Darwinian evolution, you need genetic informations. And on Earth, this genetic information is based on DNA or RNA. We see it just after. So according to this, the building blocks of life on Earth. So if we are considering the elementary chemistry, we have to focus on element, carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphate. So Sean and S and P, this is in fact the most common elements you have for life, which is in fact organic chemistry. So you have on the right here on this graph, the relative abundance of the different elements, elements here in the human body, but yeah, it's quite similar for life. So first oxygen, then carbon, hydrogen, nitrogen, phosphorus, sulfur, and also calcium in our case, because we have bones. So this is according to elementary chemistry, which is in fact organic chemistry. Then, so if we are coming back to the definition, a self-sustaining chemical system. So to have a self-sustaining chemical system, the system has to be open. So open in terms of thermodynamics means that there is exchange between the environment and life. So in order to have exchange, you have to separate interior and exterior parts. And this is, in fact, the main purpose of the cell. So life on Earth is based on a structure. For example, for the physician, the basic is atoms. For the biologist, the simple elements he will consider mainly is a cell, and it allows exchange interface. So you have here an animal cell and a plant cell. So which is important, it's the external membrane you have here, which is a border between interior and exterior. Cells are made of lipids, and lipids are one of the building blocks of life. Then, again, according to a self-sustaining chemical system, you need a production of energy, interactions, exchange of energy and exchange of matter, and in biology it is called metabolism. And for the metabolism, you need proteins, and proteins are made of 20 amino acids, and amino acids are one of the building blocks of life. Here you have a representation of a protein. So the chemical assemblage of proteins, this is really the 3D representation of protein that will allow, in fact, the chemical reaction, like a puzzle, but in 3 dimensions. You will have a receptor and the proteins will go inside. And when there is a perfect match, not so perfect, you will have the chemical reactions. So it's really due to the conformations, so to the shape of the protein in 3 dimensions. And then for the Darwinian evolution, it is necessary to have genetic materials. So for this, it's nucleic acid. So DNA or RNA, so desoxyribonucleic nucleic acid or ribonucleic acid. And it's made of sugar, nitrogen nucleobase, and phosphate group. So you have here the typical shape of DNA, and here the one of RNA. And it allows this nucleic acid storage, expression, and transmission of information, and which allow, if I am coming back to the previous slide, Darwinian evolution. So in green, you have the building blocks of life: lipids, amino acids, sugar, nitrogen nucleobase, and phosphate group. So this was the building blocks of life according to the life as we know it on Earth. So now the next step is to see if we can find this kind of building block of life in space. So what is the strategy here? So if we are going back to the formation of the solar system, so 13.5 billion years ago, it starts with a molecular cloud. This molecular cloud will collapse because this molecular cloud, which is compounded mainly of hydrogen and helium, if you have a collapse, you increase pressure and temperature. At a point, you initiate thermonuclear reactions, and this kind of force of collapsing is counterbalanced by the radiation pressure of the thermonuclear reaction, because you increase a lot the temperature. So when you reach this state, you created a star. The star is kind of equilibrium between an action of collapsing and a counterpart of radiation pressure. And around this star, you will have a disk, and within this disk, you will have the formation of planets, terrestrial one, like the Earth, and gaseous one, like Jupiter, and also icy one, we can say, for giant, for Neptune and Uranus. So it is important here to see where we can see, so to have a kind of information of the building blocks of life. For sure, we can look at the stars, because almost all of the mass of the solar system is within the star, and also to see the body, the primordial body we will have in the solar systems. So here you have a much more simple representation of the solar system with the sun and at the left, and the end of the solar system on the right. So you have also, which is called the heliosphere and the heliopause. This is the definition of what could be the border of the solar system. This is equilibrium between the radiation pressure of the sun and the one from the interstellar medium. So you see, in fact, the Oort cloud, and we are saying that the Oort cloud is within the solar system, but it's outside the heliopause. But the Oort cloud is still, in fact, in gravitational interaction with the sun. So, but the Oort cloud is quite interesting, because here you will have comets, and comets icy body that can give clue according to the initial material that forms the solar system. Another area which will be quite interesting is between Mars and Jupiter, because here you have the asteroid belts, and also the asteroid belts will have some asteroids that can fall on Earth, that will become meteorite, and the meteorite can give also clue about the original matter of the solar system. Here you have the Milky Way, so our galaxy, and also hundreds of billions of stars. So it will be interesting also to look at this star and to see their chemical composition in order to see if we have a match according to what we see of life on Earth. So if we are looking at these different objects, so first the star, and the star, we will come back to the elementary chemistry. carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. So you have here the elemental abundance in the universe, and we are looking at the stars. The stars are, in fact, the main compound of the matter in the universe, if we exclude the dark matter, of course. And so you can see hydrogen and helium, which is, in fact, the elements that have been formed at the Big Bang. And then oxygen, carbons, nitrogens, okay? In fact, we will find again the same elements that are used for life. If we remove hydrogen and helium that are coming from the primordial nucleosynthesis. So, or we can, in fact, infer this kind of composition. So again, this is interaction between matter and light. So with telescope, we can observe the stars, so the sun first, but also all the stars that are in the surroundings. So mainly in the Milky Way, and you will have some absorption bands that have features of some elements. So you will have absorption bands that are related to hydrogen, other to sodium, other to helium, and we can have, in fact, a clue about the elements that are at the surface of the different stars. So you have here a different graph chart. So with a different abundance. So, and again, if we remove hydrogen and helium, the more volatile elements that are not interesting because they are coming from the primordial nucleosynthesis, we can see that we will have again CO, carbon, and oxygen, and we will come back to the abundance of elements that are present in life. So we can do the same things, the same kind of analysis on the primordial body in the solar system. So asteroids, meteorites, and comets. The advantage we have compared to the sun, it is that it is possible to analyze on Earth some samples of asteroids, comets, and also some missions, spatial missions have been sent on this object to do a sampling and then coming back to Earth in order to analyze these elements. So this is much more complicated than only the interaction between light and matters. There is analytical techniques from laboratory that allows to detect all the building blocks of life within the primordial matter that is available in the solar system. So, which is asteroid, comets, and also molecular cloud. So here we are in the interstellar medium, so this space between the different stars. And also, so again, here we are coming back to the analysis of lights and interaction with matter. It has been detecting a diversity of organic molecules that is quite huge. So if we are doing the comparison, Earth versus space, so for the elementary chemistry, yes, there is a match between the elements that constitute life and the one we will find in space. For the cells, it's not possible to detect directly cells, but it's possible to detect lipids. For them, it's not possible to detect metabolism. It's not possible to detect proteins, but it's possible to detect amino acids, and a lot of amino acids, not the 20 that are constituting of life, hundreds of amino acids. According to the genetic materials, it's not possible to detect DNA and RNA, but it's possible to detect sugar, nitrogen, nucleobase, and phosphate group. And you can see that progressively also, when we are seeing, in fact, at this slide, there is a kind of difference between what should be a biosignature and what is a bioindicator. So the building blocks are bioindicators and not biosignature. So biosignature, we'll have a definition at the beginning of the next part. Here, for example, a cells, if we're able, in fact, to detect a cells or to see a cells, to detect a metabolism, to detect DNA. So here we have a biosignature according to the life as we know it on Earth. So here is just a kind of survey of the elements, the building blocks that constitute life. But there is also the question of the synthesis. In fact, the process that will allow us to get from elementary composition. Again, if we are going back to the guiding principle at the beginning, we say that if we have to keep one sentence according to the scientific knowledge, one sentence that can have most information is matter is constituted of atoms. But it is important to understand for the building blocks of life how we can go from atoms or very simple molecule to more complex one. And the paradigm up to the 19th century was to believe that in fact life, that is why in fact organic chemistry was developed, organic molecule was only a product of biotic product, so only product by life. And then there was non-organic chemistry, which was not related to life. And it's still in fact the case. I mean, if you're following chemical studies, there is still a strong separation between organic and inorganic chemistry. But so during the 19th century, Friedrich Wöhler, a German chemist, did the abiotic synthesization of urea. So urea is a biological product, and he was able to synthesize abiotically urea. So that is, in fact, the kind of end of this kind of conception that biological organic product indeed synthesized only by life. So this kind of experiment was the first of a lot of different synthetic experiments that were able, in fact, to produce biological molecule abiotically. Then, during the 20th century, it was the start of the prebiotic chemistry. And you have here the Miller-Urey experiment. It was realized in 1953. So this kind of experiment starts in order to understand how we can synthesize abiotically the building block of life. So this is a very simple experiment which in fact simulate the primordial atmosphere of Earth. So here the hypothesis was with methane, ammonia, water vapor, and hydrogen gas. So very different from the atmosphere we have now, which is mainly the two main compounds you have, it's oxygen and nitrogen. And they put a source of energy, here electrodes, to simulate electric arcs. And then they analyze the solution they obtain after condensation. And after the experiment, they analyze all the products of these experiments, and they found amino acids, for example. So it was possible again to produce abiotically some compounds that were known to be essential for the development of life. So for the second part, again, there is a kind of opposition between that the building block of life widespread. They are quite common in the universe, but we don't know yet how to use, in fact, these building blocks to have really life. So there is a kind here of something which is not known. It's how we can go from building blocks of life to life. So this is the end of the second part. Do you have any question? No? So now, detection of biosignature. So again, we need to define what is a biosignature. So it's possible to use the definition of the NASA. And NASA says that a biosignature is any characteristic, element, molecule, substance, or feature that can be used as evidence for past or present life. So, yeah, so it's quite not so precise. So if we are going back, for example, to what we are saying according to the building blocks are not biosignature in this case because they are not indicative of life. They are bioindicator. But for example, if we detect cells, metabolism, DNA, so genetic material, here, yeah, the life as we know it on Earth, this is a kind of indubitably, this is a kind of biosignature. We are sure that if we find this kind of signature on Earth or another body, it's characteristic of life. We have also this kind of chart here in order to summarize scientifically this kind of definitions. So the different scale at which we can detect life, also the instrumentation we can use, and the different compounds, in fact, you are looking at in order to detect life. So then we will see different examples to illustrate the fact that it is in fact very difficult to detect a true biosignature. And we will start in 1980 with Mars, with the observation by telescope of the planet Mars by Schiaparelli, so an Italian astronomer, and he made a map of Mars, and he was using, in fact, the term canali, which means channels. So there was a kind of misunderstanding according to this translation, particularly, for example, in France, when they use the terms canaux, which is artificial channels. So there was, in fact, the kind of feeling that on Mars there was a kind of civilization. So here we will shifting a little bit from biosignature to technosignature. This is the only time in the presentation I will speak about technosignature, because this is a kind also of important development in the field, which is led by the SETI Institute. So SETI search for extraterrestrial intelligence, mainly in radio astronomy. So they are trying to detect signal that can be emitted by civilization, technologic civilizations. So this is quite different from biosignature, but this is also a part of astrobiology. And in 1990, with the channels, the canali, this was a kind of technosignature. So of course it failed. So there was other observation with a better telescope of Mars, and also Mariner 4. I didn't remember the exact date, perhaps it was in the 70s. And or the 60s or 70s. So this is the first picture of Mars, and of course it was the end of the belief that there was a kind of civilization on Mars, because the pictures were showing an arid and dry world. So we stay on Mars, and in 1976 with the Viking, and what can be said about Viking, that this is the first death of astrobiology. This is quite important, this Viking missions, because it was really a biological mission. The aim was really to detect life on Mars. So there were a lander and an orbiter. Here you have the orbiter with Carl Sagan. We'll speak about Carl Sagan at the end of this talk. And there was three main experiments, which is the pyrolytic release, label release, and gas exchange. So the aim, the philosophy of the experiment was to feed a potential biosphere on Mars with radiogenic, in fact, carbon nutrients, and to see then if, according to the product we will see, we can detect this kind of radioactive activity, which the meaning of that is that the nutrient was used by the biosphere to product so secondary products that can be analyzed just after. This was a kind of philosophy. So you have here the kind of conclusion of H.P. Klein, which was the PI of the mission. So the essential finding of the three biological experiments about the two Viking mercenaries, because they were two Viking in two different places, are reviewed and compared. Most of the findings, however, are inconsistent with a biological basis. The combined data suggests the presence of several classes of oxidants on Mars, and this would account for the most of the observations. So this is quite important, these Viking missions and the failure of this mission, because then the strategy to go on Mars was not with a biological objective, but much more a geological one. And I think Fulvio is quite happy with this. So it was much more than a kind of geological study of Mars, which could be also relevant to, according to biology, for example, with the study of the habitability. But let's say that the paradigm changed with the failure of this Viking mission, and the mission shift to biology to geology. Because with geology, success is obvious. So there is still controversy according to the analysis of the result of the Viking experiments, and 20 years after, at the beginning of the new millennium, there was new analysis of the label release by a Mexican chemist. And but he explained it abiotically. But for few people, it was still an experiment that was the proof of life on Mars. But I say failed. So here you have a huge gap, but we are still on Mars. Alors, indirectly, we are in 1996. ALH 84001, astrobiology is back. And this is the analysis of Martian meteorite that have been collected in Antarctica, Allan Hills, which means for AL. And so one team shows this kind of picture, I think, which was taken with electronic microscope. And you have this kind of structure. So on what they focus on magnetite and macroscopic tubular structure. So here it's a kind of morphological biosignature. So for them, it was really similar to some structures that are really characteristic of life on Earth. And they say that it was kind of relic of life from Mars. But then there were lots of different studies, and the conclusion was, in fact, it was not biotic origins, but an abiotic one, which produces this kind of morphological biosignature. So again, it was a failure to detect a biosignature outside the Earth. But we are in 1996, and something which is quite important, we are very close to 1995, and you have here a kind of representation of radial velocity detection, because 1995 is the first detection of an exoplanet, so a planet which is orbiting around a star which is not the sun.
Adrien?
Yeah?
It's been 1 hour, eh?
I'm almost done.
Okay, okay.
So then we have the methane. So detection of methane again on Mars, 2003. So here first by telescope. They use telescope to see distribution of methane. So you have here. So if you're looking the map, it could be quite important, in fact, source of methane, but it's ppb, and it's part per billions. So it's very small concentration. Then it was confirmed by confirmed by curiosity, even if we can say a lot according to this curve, according, for example, to the uncertainty you have for the different points. And so the ESA launched a mission, TGO, Trace Gas Orbiter, in 2016, in order to detect methane, and the probe was not able to detect methane. So there was a development of kind of scenario to explain this kind of methane emission, because normally after the emission of methane, it will disappear very quickly in the Martian atmosphere. So if you can detect methane, it means that there is a kind of a source that can sustain these concentrations, even if it is very low. But now even the detection is controversial. So people say that perhaps there is a kind of contamination for the rover, and that the analysis is it's too low in order to be considered, according to the ones that have been made by telescope. So this is still a controversy, so not a failure, but yeah, the tendency is that methane on Mars is improbable. And the last one, 2020, the phosphine on Venus. So phosphine is pH3, it's here. It was also very controversial, and most of the studies that there is no phosphine on Venus, and if there is phosphine, it's abiotic origin. But this is something which is really interesting, because we are not seeing a kind of biosphere on the surface, but in the cloud. So we are in a very particular world. Venus is a very strong atmosphere. So at the surface, you have 400 degrees Celsius. So the habitability for Venus here is in the cloud. And you can see here we have methane, water, and phosphine. So phosphine, which can be a byproduct of biological activity. So this slide is still controversial, phosphine detection on Venus. It's also to show that we can find biosignature not only on the surface, also in the atmosphere. So here we don't have a success for biosignature detection, but there was in fact one success once, and it was here. It was a work of Carl Sagan. He used the Galileo flyby in order to look at the Earth as a planet, and it detect the chlorophyll, oxygen for sure, and atmospheric methane. And this is a kind of sort of development of to find biosignature, to see the Earth as a celestial body or as an exoplanet. You have an example here in order to see what will be the spectrum of the Earth with or without cloud. And something which go beyond, in fact, biosignature, it's the observation of the breathing Earth. So we are coming back to the initial slide at the beginning. So you can see here the development of snow ice in the high latitude, the development of the vegetations on the continent, and also the phytoplankton bloom in the ocean. So this is a dynamic process. So we go to agnostic biosignature, the dynamic behavior of life could be also a way to detect it on exoplanets or in other bodies. So yeah, this is coming back, in fact, at the beginning of the presentation with chlorophyll, photosynthesis, which might be a way to detect biosignature on other worlds. So for detecting biosignature, still no, it's a failure, or there is a lot of controversy according to the one that were not failure. So to finish, conclusion, contingency and the Fermi paradox. So the contingency, it's a way, in fact, to balance the fact that if we are considering the universal law of physics, that the building blocks of life are widespread in space. But normally we have to say that life has to emerge naturally, let's say, in the Milky Way and in the universe. But then there is a kind of counterpart of the contingency. The contingency is considering not the universal law of physics or chemistry, but also the natural history, all the steps that allows the life to appear on Earth. And if you are considering all the history, the giant impact of the moon, of the Earth and planetesimal that form the moon, and then also the typical configuration of the solar system with Jupiter and Saturn, two giant planets that are similar in size, that avoid to have this kind of migrations in the internal part of the solar system. And you can continue then with the development of life on Earth. There is a kind of feeling that life might be very rare because it needs environment and contingency that are quite exceptional. And then the Fermi paradox. So Fermi was a physicist of the 20th century, is to say that, okay, beyond life, if there is other civilization, why this civilization were not able to contact humans on Earth? So you have three, in fact, solutions for this. They are rare, they are undetectable, they are isolated, or they are dead. So most of the reflection in the scientific community is going to they are dead. In fact, the evolution is quite long of life to reach complexity. And so the time, according to this development, according to the time of the lifetime of a civilization, the order of magnitude is completely different. So you can have a development of different civilizations in the galaxy, but they will not have time, in fact, to meet. This is a kind of one of the solutions of the Fermi paradox. And there is also the Gaian bottleneck. Life commonly arises but cannot be sustained because you need stable conditions for life to stay in time, to stay in time. And perhaps this is a huge limiting factor. So you can have, for example, development of basic life, unicellular organism, but the condition will change on the body and it will not be possible, in fact, to sustain life. So I will not speak about this article, but it's quite interesting. It's about the Gaian bottleneck applied to Mars. That it could have been the apparition of life on Mars and change the condition on Mars and make Mars inhabitable. So it's quite interesting, and it's also a Gaian bottleneck. So last but not least, according to biosignature, this is a quote of Carl Sagan, absence of evidence is not evidence of absence. And of course, it is important to continue to try to find biosignature. So if you have any question,
Adrien, I would like to know, what is your personal view?
Okay. So my personal view is, it's an opinion. It's not scientific, because I have no real argument. Let's say that I can go into matter and try it to test my hypothesis. But I am going into life commonly arrived, but cannot be sustained. So I think if we will find some biological signal, it will be related to microorganisms. So basic life. I have lots of doubt according to other civilization and so on. So because of contingency and this kind also of Fermi paradox. But again, this is an opinion. This is not. I cannot prove it.
Thank you.
Can I ask something?
Yeah, for sure.
Yes. Oftentimes when extraterrestrials are being looked at, we often hear of the term Goldilocks. Goldilocks, I think that is the term that seems to be considered as a precondition. Is there a significance to this Goldilocks, which is often referred to?
Okay,
Thank
so
you.
I think according to the Goldilocks, you are speaking about the habitability zone, no?
Yeah, exactly. Is it a precondition for biosignatures?
So yeah, no, but it's a very, very interesting question. I didn't speak about it because it was quite long. But yeah, so I focus on the building blocks of life. But of course, if we are looking at the life as we know it on Earth, we need a solvent. And the solvent which is present on Earth and which has amazing characteristic is liquid water. So liquid water seems to be something which is necessary for the development of life. And according to the search of life in the universe, this is a common strategy to use the habitability zone. So which is the zone in which you will have the probability to have water at the liquid state. So I have a specific slide for this. Yeah. So water and habitability zone. So this habitability zone, which is not habitability, it's liquid water zones, depends of almost only on the stars you have in your system and the distance from the stars. So if you have big stars, blue stars that are quite energetic and they are high temperature, the habitability zone will be farther in the stellar system. If you have a cooler stars, you will have an habitability zone which is closer to the star. And then all we can in fact do the modelization of this variability of the habitability zone, it's according to the atmosphere. You know that according to our atmosphere, we have gas like carbon dioxide, so which increase the temperature. So astronomers and geophysicists, they can make, in fact, a modelization to see in which intervals we can have liquid water on the surface, because this is the basic hypothesis. It's liquid water on the surface according to the atmospheric composition. So typically, the inner part is rich when you put all the water in the vapor state. So then you have a kind of Venus. And for the outer part, it is when the gas of the atmosphere will condensate in the upper part of the atmosphere. That is why, in fact, you can have an uncertainty according to the habitability zone. But this is for the search of life in the universe according to the exoplanets, something which will be used a lot to define, to do the prioritization of observations according to some planets that are in the habitability zone. So this is an incomplete concept because if we are looking, for example, at the solar system, we know that beyond the habitability zone, we can have bodies that can have liquid water. For example, the icy moon, Ganymede, Europa, Callisto, Enceladus, Titan for the Saturn system. So you can have this kind of icy moon, which are also ocean world. So the concept of habitability zone is limited, but this is a good tool in order to select some interesting world in our stellar system, and then we will have the capability to analyze the atmosphere of exoplanets or terrestrial exoplanets. Now we have the capability with GWST to analyze gaseous atmosphere, but it will be possible to analyze the atmosphere of these terrestrial planets that are in the habitability zone and try to detect thermodynamic disequilibrium between gases, and it could be an indirect biosignature. So yes, this is an important concept for biosignature detection, which is based on the presence of liquid water on the surface.
Thank you.
Oh, hello again.
Yeah.
Thank you very much for your nice talk. But we have a number of questions from the chat. One of them is, what are allotropes?
Can you repeat again the question?
What are allotropes?
Ah, allotropes. So Fulvio might correct me according to the allotrope, but this is the same chemical compounds, but which we have a crystallizations form which is different. So the example I have in mind, for example, it's diamond, so which is a crystal made of carbons, only of carbons. So we can crystallize like a diamond or like a graphite. And graphite is the stable phase at atmospheric conditions of carbon. So this is the same chemical composition, but the crystal structure, the way the atoms will arrange in space are different. Fulvio, you can confirm it?
Yes, yes.
Oh, all right. Thank you very much. The last group of questions from the chat is, why do some scientists think the perfect star for life is orange dwarf? Is unknown compound in Neptune atmosphere an organic compound? Do you believe in omniverse or multiverse? Why or not? Thank you.
So there is different. There are different questions, no? So perhaps so the last one is according to multiverse and universe. So this is interesting theoretically. So the people who are doing cosmology, in fact, theoretically, it's possible to have multiverse. Then I can come back, in fact, to the guiding principle of science. This one, a cognitive exploitation of scientific knowledge. There is a step of materialism, so experiments on matter and its emergent property. The problem with this kind of multiverse hypothesis, it is we cannot do a test on it and we cannot have observation on it because it would be, for example, an universe which is outside our own universe. So no, we don't have the capability to test this kind of hypothesis. So we are going outside science. So theoretically, yeah, it's feasible, but we don't have the experimental or observational counterpart. So we are going outside science there. So perhaps we will have a way, in fact, to test this hypothesis in the future. But now, yeah, it's we don't have the observational or experimental counterpart. So this was the first question, and then there was another question about Neptune.
Yes, is the unknown compound in a Neptune atmosphere an organic compound?
Here I don't know. According to the gaseous planet on Neptune, I really don't know. So this is the icy giant. So this is not really like Jupiter and Saturn. Uranus and Neptune are quite different. Organic have been detected there, but then yeah, this is a kind of complicated medium because you have a huge atmosphere and so, but there is still ongoing, in fact, interest for the outer solar system, not only for Neptune, also for Pluton and Charon. But I am not specialist at all of this system to answer this kind of question.
All right, thank you very much. I think we have gone a bit beyond the time we had hoped for. I will turn it to Fulvio and maybe Gihan. Thank you very much.
No, I have nothing to add. It's already very late. Thank you, Adrien, for your presentation.
No, but you are welcome. It was a pleasure. Thanks for the invitation again. And I hope, yeah, to meet you perhaps in Botswana.
Okay.
Oh, wonderful. That would be nice.
Prof. Modizi, over to you.
Oh, Fulvio, yeah, no, thank you very much, Adrien. This was a fantastic talk. Yeah, I think, yeah, we have come more or less to we have used over time, but that's because the talk was very interesting. So thank you, and we wish you and welcome you to Botswana when you are able to. Yeah, thank you.
Okay, but you are welcome.
Ciao, ciao. Ciao, ciao.
Ciao.